Okay, our next presentation today is from the Mechanical Engineering Department and is titled Biomechatronic Foot. This project is a prototype of robotic foot that works like a human foot for applications in humanoid, robots, and prosthetic feet. By studying human walking and foot movements, the team created a robotic foot that can emulate a human foot with sensors to help it stay balanced and move in different ways. And now I invite the mechanical engineering team to share their presentation. Please.
Thank you. Hello, everyone. We're the Biomechatronic Foot team here at Cal Poly Pomona representing the ME department. My name is Jason. That's Jason. We've also got Chris and Ryan up here, and our other two fellow members, Dylan and Adrian over there, and our project advisor, Professor Carlos Castro. And today, I'd be happy to talk to you about our foot. Now, the objective of the Biomechatronic Foot project is to investigate and develop a more dexterous biomechatronic foot compared to the current flat-footed rigid models used in robotics and prosthesis today. We began this with a study of the human foot's anatomy, kinematics, and function, which we used that knowledge to create our design. And once that design was finalized, we simulated the movements using sensors and microcontrollers. Starting with the relevant anatomy and kinematics, you could basically break the human foot system up into three subsystems, that is the ankle, the toes, and the midfoot. Starting with the ankle system, the ankle provides 2 degrees of freedom, as you can see in the diagram, and functions to move the foot as well as transmit power via the Achilles tendon. Moving on are the toes or phalanges, which provide 1 degree of freedom per joint and function to provide balance as well as propulsion in the walking gait cycle or when you take a step. These are actually all actuated together by a single strand of tendons. And finally, we move on to the midfoot, which can be seen as a series of arches that flatten out to absorb impact. With all this in mind, we move on to our design.
So this senior project is actually a continuation from the previous academic year. So we actually had some information and models to get ourselves started. The previous design could be seen on the left side of the pictures, while our design is shown on the right side of the pictures. Ultimately, we decided to use a completely new design, mostly because of different actuation methods. They decided to use pneumatics, while we decided to use electronics. The design process for the tibia, or the shin, and the midfoot started with some hand-drawn sketches. After that, we created some initial models that were very blocky and unnatural looking. After many iterations, we had a model for both the tibia and the midfoot that looked a lot more like what a human leg looks like. When compared to a 5-foot, 10-inch tall person, our biomechatronic foot is actually fairly close in size. Our estimated weight of about 12 pounds is also fairly close to what a 175-pound person's lower leg would weigh, which is about 11.5 pounds. So our design actually isn't that far off from what an actual human leg would weigh. For actuating our model, we decided to use an Arduino Uno microcontroller, 2 button-controlled linear actuators to act as the Achilles tendon for the heel, and 2 cable-driving servos for the toes. The PA15-4-33 linear actuators were chosen due to their force output, their stroke length, as well as their operating speed. The DJI DS5160 servos were chosen due to their torque output, as well as their operating speed. To sense our foot's position as well as its movement, we decided to use an IMU, or an inertial measurement unit, which has both an encoder, or which has both an gyroscope as well as an accelerometer, and this was placed within the midfoot. For each of the toes, we also included a Born's 3382H encoder, which allows us to measure the angle of the joints for each of the active toes whenever they're actuated.
So for the range of motion regarding the ankle, 2 linear actuators were actually used. In addition, with a universal joint that offers 2 degrees of freedom, this allowed the foot to follow the 4 main movements of plantar flexion, dorsiflexion, pronation, and supination. as you can see in the video above. These slides go over a more detailed image of each movement. At its neutral position, the foot will be at a 90-degree angle with both actuators actually extended 3.67 inches. For the plantar flexion, the foot will be at a 60-degree angle with both actuators retracting to 1.4 inches. And for the dorsiflexion, the foot will be at a 40-degree angle with the actuators extending to 4.9 inches. For the pronation and supination, both actuators actually act independent from one another. So for the pronation, the actuators are actually 1 inch offset from their resting position, which allows the foot to angle to the right at a 24-degree angle. For the supination, it's basically the opposite, with the foot angling towards the left at a 24-degree angle as well. For the code, it primarily relied on the IMU readings. This IMU reading for the plantar and dorsiflexion started at a 90-degree angle in its readings at its resting position. However, when the actuators either extend or retract, the value of that 90 degrees will reduce because of how the IMU is set up in the midfoot. As such, when the button to perform plantar flexion is pressed and the IMU reading is greater than 60 degrees, both actuators will actually retract until 60 degrees is met in the IMU reading. Likewise, for the dorsiflexion, if that button is pressed and the IMU reading is greater than 40 degrees, both actuators will actually extend until the IMU reach 40 degrees. For the pronation and supination, it is a little different with the IMU reading, as it actually starts at 180 degrees. And for that, when, for example, the button for the pronation is pressed, and it's greater than 156 degrees, the left actuator will actually retract, while the right actuator extends until 150 degrees is met. For the supination, all the values in the IMU actually turn negative. As such, when that button is pressed and the IMU has a reading of greater than negative 156 degrees, the right actuator will actually retract while the left actuator extends until that desired degree is met.
All right, so moving on to the design of the toes, one of our main design goals was to create a more anatomically accurate design for our toes. And to do this, we decided to run all of our actuation cables and sensor wires through the inside of the toes. So in our initial drawings, you can see how we planned on routing those cables. Moving on to our initial models, we initially started out with blocky designs as with the tibia, but slowly sculpted them down to be in more natural shape. This is also when we realized that we have the space and ability to add additional toes to reach 5 toes like most of us have. When we did this, we elected to keep the 2 additional toes shown in white, passive, with nitinol wire running through them. And nitinol is a nickel titanium alloy that is just very flexible and provides good stiffness passively. The orange toes are actuated together in parallel, and the active joint is the second joint shown in the toe, while the red toe, or big toe, is actuated at the first joint. The range of motion we're able to achieve with the toes occurs using the 2 servos found at the top of our foot and with cables running the length of the toes in a pull-pull mechanism. The passive toes, as I've mentioned, are passive using nitinol wire, but this also occurs at our passive joints as well in the active toes. The encoders housed in each toe act to give feedback for our motion when we actuate our toes, and as you can see from our plot, we're getting between 30 and 40 degrees of actuation per cycle, as shown in the video. This is slightly less than our maximum designed range of 63 degrees, but this is due to that nitinol wire in our passive joints. Another thing we added to our toe was our foot was a heel damper to absorb impacts and shocks during the gait cycle. And we did this by printing a thermoplastic polyurethane block, or TPU, which is a 3D printed flexible filament at different infill densities using the hexagon infill. We elected to use a 15% infill density because at about 0.1 or 0.2 inches of deflection, this would take around 60 to 120 pounds of force, which seems reasonable for the average human. So, our final results. Our biomechatronic foot has a 3D printed tibia housing that houses all of our sensors, electronics, and processing. The ankle has a 2-degree of freedom U-joint and is controlled with our IMU housed in the midfoot. The linear actuators are activated with buttons, and our toes are controlled with the servos housed in the tibia. And finally, our total cost was around $515.
Moving on to future improvements, we'd like to see that the heel get redesigned to allow for a better range of motion in supination and pronation, as well as redesigning the shin box to better fit all of our electrical components. We'd also like to troubleshoot the actuators to allow for compound movements, as well as adding encoders and rod ends to allow for better sense data. Finally, we'd also like to see force sensors added to analyze the forces through an actual walking gait cycle, which would be the next step in simulating human movement throughout this project. We'd like to give special acknowledgements to David LaFay for machining our parts, acknowledgement to Provost Teacher Scholar Support Program for their financial support, and finally also our project advisor, Professor Castro, for guiding us these past 8 months and letting us work on such an interesting project as we end our college careers. Thank you.
Thank you, ME team, mechanical engineering.